So, in the last of our lectures on linear momentum and collisions, we're going to expand our last analysis into 2 dimensions and deal with 2D collisions. So in a 2-dimensional case, essentially this is very much like kinematics, and really what we're doing is taking our 1-dimensional case and expanding it into 2 dimensions. So for a 2-dimensional case, not only are we dealing with momentum in the x direction, but we'll also deal with momentum in the y direction. And remember, momentum is always conserved. It doesn't matter if it's in the I or j, let's go that way, or k, or the x, the y, and the z directions. The momentum is always conserved. Just do not mix up your x velocities with your y velocities, and treat each of them discretely. So, in terms of our momentum for an elastic collision in the x direction, we'll have m1 v1 in the x direction plus m2 v2 in the x direction, and that will equal a final momentum in the x direction, 2 discrete values. The same for the y direction. Most realistic bodies, you'll end up with bodies moving in separate directions after a collision. Most realistic collisions, I should say. That's referred to as a glancing collision. So take 2 pool balls that hit one another. If they're deflected through some angle after the collision, then what we'll have there is a glancing case. Now remember, there's the diagram for a 1D elastic collision. So this is the kind of thing I'm talking about. Here we had an arrangement of pool balls. The cue ball came in, hit these balls, and they all went various different directions. This is what we refer to by a glancing collision, and the angle here can be easily seen. So a glancing collision between 2 bodies will involve one body coming in with momenta and hitting the other. Now this is 2 balls essentially viewed from above. Invariably, when I see a question like this on an exam or on an assignment, someone always says mg is acting this way. This is not the case. This is a flat plane like a sheet of paper or a table viewed from above. So what will happen here is body 1, the yellow one, will come in and hit body 2, the red one. They'll collide and they will move off in separate directions. That means we can define 2 angles here, theta and phi, from some midpoint. Now there's a very special consideration. If 2 objects are of equal mass and they come into one and hit one another in a glancing collision, then one of those objects is already at rest. So one object is standing still and another object comes in and hits it. Both of them are the same mass. The 2 objects will always move away from one another with a total angle of 90 degrees. So what do we mean by that? That means in this case, M1 here has come in and hit M2, the red ball, and they've bounced off one another. After the collision, M1 is moving at angle theta, M2 is moving at angle phi. That means theta plus phi is 90 degrees. Not 2 90s, because this would be 180 and they would be bouncing up and down straight. That can happen, I suppose, in some cases, but very weird if it's coming in from the x direction. It would mean that this total angle theta plus phi is 90. That would mean this might be 60 for theta and 30 for phi. Now if we do look at conservation of momentum in 2 dimensions like this, if one object comes in and hits the other and they bounce off, what this means is we'll have an x and a y component to each of these velocities. This means we'll have, for our momentum, m times v1f sine theta in the y direction and m times v1f cos theta. We'll also have a set of v2s of cos phi and sine phi. Note These two objects have undergone a collision and they're moving to the right. That gives them an overall positive velocity in terms of cosine theta and cosine phi. But this object is moving downwards compared to this one, meaning it'll have a negative attached to its v2f sine phi. If we resolve the momenta, it'll look something like this. We could say that m1 v1i here, because this object was moving, these were standing still, will be m1 v1f cos theta plus m2 v2f cos phi if we're looking in the x direction. Likewise, we can say in the y direction, the momenta would be m1 v1f sine theta plus m2 v2f sine phi, and that should be conserved. So if we subtract the two, we should get a total momentum of 0. So we've said this before, if we apply conservation of momentum, we can get our angles. We can wind up with m1 v1f sine phi sine theta and cos theta cos phi. We can also do this in terms of kinetic energy. And remember, this is really the same thing, just with factors of half mv squared involved. The collision is elastic, so v2i is 0 though. Conservation of energy applies as well as conservation of momentum. Consequently, we can say KEI is equal to KEF, just as initial momentum equals final momentum. So here's a quick question. Pool ball comes in, hits the 8 ball. They bounce off of one another. The cue ball bounces off at 35 degrees. What angle is the 8 ball deflected at? We're saying that these things are not rotating, so don't worry about losses due to rotational motion. That's irrelevant. And we're going to say what is going on here in terms of the angle. You should immediately say that this angle here, theta, is 55. If this total angle here is 90, this is 35, this theta here should be 55. Hopefully someone's not trying to play you. So these balls will both be the same mass. If we analyze this a bit more, we can draw this as a diagram. We're saying if one angle here is 35, angle theta here is unknown. Target is at rest, v2i is 0. So if we make a statement of conservation of energy, and we write that out as half mv squared, here's our initial equal to my final. All the kinetic energy is coming from one ball, but then it's spread between the two. So by conservation of energy, this is how our equation will look. So m1 is equal to m2 though. That means we can eliminate the mass in our equation and create one equation in terms of initial velocity and final velocity. By conservation of momentum, this must be true. We can square both sides of 2, and you can see this is going to look very familiar here. v1f squared plus v2f squared plus plus 2 v1f, sorry, v2f. Rearrange this, and we can put this in terms now of our x direction. So we'll end up with equation 3. Now let's take equation 3 and do something with it. Let's subtract 1 from 3. This will give us this solution. This, remember, is going to come from here. And it'll give us this. 2vi times v2f cos theta plus 35 is 0 for a conserved energetic case. Taking that now, we can say cos theta plus 35 is equal to 0. That means theta plus 35 has to be equal to 90. So theta is 55 degrees. That's a very long-winded way of going about this and ending up with the answer of 55 degrees. I tend to just remember the total angle is 90 degrees. And that means that if we've got 35 degrees for one proportion, 55 is for the other. But you can derive it should you feel the need. But mathematically, that means that masses that are equal will always move at 90 degrees to one another after a collision that is elastic. So that's an elastic case, a very specific elastic case, where the masses are equal and one velocity is zero. If we look at an inelastic case, let's take a look at a car crash. So in this particular case, we have a 1500 kilogram car, excuse me, and this car is traveling east at a speed of 25 meters per second and colliding with a 2500 kilogram car traveling north at 20 meters per second. We want to find the direction and magnitude of the velocity of the wreckage after the collision. We're assuming these vehicles undergo a completely inelastic collision. What we mean by that is there's two discrete masses with two discrete velocities before the impact, but two masses added together times some common velocity following the impact. So car 1 here at 1500 kilograms and 25 meters per second, and car 2 with 2500 kilograms moving at 20 meters per second. They will come together, crash. Don't worry about them spinning or anyone taking avoiding action, and they will move off at some angle theta after the crash. Now, think about this carefully. What's really going on here? Car 1 is moving east, car 2 is moving north. That means that car 1 is bringing all of the x momentum to the party, and car 2 is bringing all of the y momentum to the party. The fact that neither of these people take avoiding action and are pretty stupid actually helps you in this calculation. Because if they did take avoiding action, you would end up with a number of different trig terms to play with. But they don't. So they hit one another at their center of mass and move off at angle theta. So there's our situation. There's the diagram you'd want to draw for yourself. And remember, we're trying to say that momentum is conserved, that Pi, initial momentum, is equal to Pf, final momentum. So only momentum in the x is from car 1, and all the momentum in the y is from car 2. So the momentum in the x direction will be just the initial momentum from the x direction. So that means car 1's initial momentum. Remember, that's going to be 1500 kilograms, his mass, times 25 meters per second. That's going to give us 3.75 times 10 to the 4 kilogram meters per second. The wreckage then moves at angle theta. That means the wreckage afterwards is going to move at some pxf, some final momentum. This is going to be 4,000. Now that's 4,000 here because this is the 1,500 kilograms of car 1 added to the 2,500 kilograms of car 2 times the final velocity, which is going to be some new velocity vf, times the cosine of theta because it's the x component of this velocity at an angle. This means the total momentum in the x direction is always constant, pxi equals pxf. So we can set equation 1 equal to equation 2. So we can say 3.75 times 10 to the 4 kilogram meters per second is equal to 4,000 kilograms times v cos theta. And we're saying this is equation 3. This means we can do the same in the y direction, and that all the momentum in the y direction is coming from car 2. So Pyi equals Pyf. Our statement of conservation of momentum should be made for every single problem that we do, as a reminder to me and a reminder to you. So That means 2500 now, multiplied by 20 meters per second, will give us 4,000 kilograms times v sine theta. Sine theta, because now we're looking at the y component through the angle. That means we have 5 times 10 to the 4 kilogram meters per second, and this is equal to 4,000 times v sine theta, and we're calling this equation 4. So the final momentum is a proportion of x and y. It'll be partially momentum in the x and partially the momentum in the y. So what we can do is divide equation 4 by equation 3, essentially saying that the proportions will be this equation divided by this one. That means we'll have 5 times 10 to the 4 divided by 3.75 times 10 to the 4. And this will be equal to 4,000 v sine theta over v cos theta. That's about the simplest trig term we could possibly come up with, because now, if we do sine over cos, we'll get tan. You could do cosine over sine, it wouldn't matter, but it makes our life easier to just get a tan function out of this. So, what we can say now is tan theta is equal to 5 times 10 to the 4 over 3.75 times 10 to the 4, which will give us an answer of 1.33. So essentially, if you look at a question and says find the magnitude and direction of the momentum, you really have to find the direction first to plug back in to find the magnitude. So inverse tan of 1.33 will give you 53 degrees. And now we can go back to 4 and sub in for theta. So now we have a complete equation. 5 times 10 to the 4 kilogram meters per second will be 4,000 v sine 53. That gives us a velocity of 5 times 10 to the 4 over 4,000 sine 53, which will give us 15.6 meters per second. So finally, the last part of our discussion of linear momentum and collisions is center of mass. And we're going to discuss center of mass a little more in the next section. For a system of particles, any system of particles, if they are interacting, they will behave as if all the mass is concentrated at some specific point. If you think about what that means if something is subject to an acceleration, albeit a force, that will change how it behaves depending on the distribution of matter. So take these two objects. Here we have M1 and M2. As you can see, M2 is bigger than M1. We're assuming they're the same density. Therefore, the center of mass of this system would locate somewhere towards M2. That means we can now have three possible definitions of distance. x1, a distance from the origin to M1, x2, a distance from the origin to M2, and the center of mass, the distance from the origin to the center of mass. This means you can define three different distances. The distance here from the object to the origin, the distance from the object to the center of mass, the distance of the center of mass to the origin. This really boils down to a relatively simple equation. The position of the center of mass is basically a weighted average of two masses. So the position of the center of mass will be whatever the original mass is, so m1 times x1 plus m2 times the position of m2, x2, divided by the addition of the two masses. So for x1 being at the origin of 0 and x2 being at some distance d, if mass 2 is equal to twice of mass 1, you'll end up with a simple calculation of saying that the distance to the center of mass here would be 2/3 d, where d would essentially be the distance to x2. from the origin. The center of mass, of course, really does affect the dynamics of an impact, or how a force is applied to an object. So take this for example. Here we have a dumbbell type shape. We have a large mass here and a small mass here. The center of mass is located here, towards the larger of the two masses. If we apply a force here to the top just by the smaller mass, we will end up with the system undergoing a rotation. Doing the same again and applying a force towards the larger of the two masses will again result in the system rotating. It may also translate in the x direction, but it will definitely rotate. If we wanted to move this object without rotation, we would have to push at exactly the center of mass. So here our force is applied just at the center of mass. The center of mass equation can be applied to any number of masses. You could apply this to one mass, 2, 3, 4, 5, blah, 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 as complicated as you would like. So essentially, m to the n, x plus times x to the n over the sum of all the masses to the n. Consequently, this can get very, very complicated very quickly, especially if you're trying to do some transformation during a collision, which requires multiple masses. And this usually results in a computational problem, which up until recently would not have been solvable without computers. Consequently, we will not really be dealing with anything more than two objects that will be colliding, especially when we start to talk about the center of mass. So, ignore this page number, this is from a prior book. One of the things that can be done is looking at collisions in the reference frame of the center of mass. The dynamics here are exactly the same as looking at one object relative to another object hitting it and looking at those impacts. The only thing you would have to do is compensate for the distance from the center of mass to the two objects, which really becomes a relatively simple transform of saying u, which is the position of the center of mass, the velocity of the center of mass, would be the velocity of the object minus the velocity of the center of mass, because the center of mass itself will be moving along with the objects. Consequently, the colliding objects in center of mass reference frame will be mv again, but now it'll be this u value, this difference between the velocity of the object and the velocity of the center of mass. So for head-on elastic collisions, u1i will equal negative u1f. u2i will equal negative u2f. So this is what we mean. If the two objects here, v1 of m1 and v2 for m2, are moving left to right, the center of mass will move with them. If this object is moving towards this object, then the center of mass will stay within the middle and move just a little bit and get closer and closer to both of these objects. So essentially, your center of mass reference frame is the same calculation again if we're talking about C of m. So m1 v1 plus m2 v2 over m1 plus m2. The only thing you'd have to do is introduce this translation of u1 and m2 and u2.